So to quickly recap what we had covered in the last online class, which is actually available online. But anyways, we had actually finished our discussion on virtualization technology. Okay. So just to quickly recap the whole chapter itself and not just what we had covered the last time, just to remind you all, the important takeaways is you need to have an understanding of, like, formally speaking, what is the concept of virtualization, right? What is the motivation behind it? Always keep that in mind, why people came up with the idea of virtualization technology. Then there are different abstraction layers of virtualization. Okay, that's what we mean by abstraction layers, where or how you can actually implement virtualization on different layers of your computer systems. So keep an overview of where those layers are and what does virtualizing in those layers mean, right? To have an understanding of that. Then basically there was a talk about performance analysis. So in terms of different performance metrics that was there, like how costly it is to implement the virtualization technology, how much application isolation do you get, how much application flexibility do you achieve if you apply virtualization to the different layers that are available, right? So keep an understanding, you don't have to memorize that, but have an understanding that, okay, if I take all of the different metrics in average, right, what is the output, right? What is the top, what is the bottom, right? And what are some of the niche cases of virtualization that can be available. So for example, what I mean by niche case is that there's a thing called instruction set architecture, right? And you can apply virtualization for that. That is not something that you see that often, right? So you need to know, like, when could it be useful, where do you apply it, and things like that. So that is how you prepare when you grasp your knowledge, right? You don't just memorize, oh, this is the definition, this is what it is. But you need to know that given that this is the definition, how would you consume that information and apply yourself? That is the most important thing, right? So that is how you need to prepare when you approach these kind of things, right? On top of that, we also talked about things such as how do you perform CPU virtualization, how do you perform virtualization on the memory, and how do you perform IO virtualization. So get an understanding of this. In addition to this, you also need to know the comparative study that we did between OS level virtualization and hardware level virtualization. Okay, and how this discussion led to a new concept, which was essentially adopted by cloud computing, which is hardware assisted and then software implemented virtualization. Okay, the software implemented is not a part of the the terminology itself. It's just called as hardware assisted virtualization. But essentially, you have to remember that it is still implemented through the software. And that brings us to the final most important thing of that particular chapter is what are the different functional architectures that are available for our hypervisors. Okay, and these are essentially of two types. So you can either have the microkernel architecture, or you can have the monolithic architecture. Okay, and when you're preparing, you need to know what these are, what are its distinctive features, how do you differentiate between them? That is the most important thing. You need to know the architecture itself, that how you're implementing. So all the discussion that we had with respect to having a domain 0 and a domain U, where the domain 0 is basically the admin VM, and then the admin VM is responsible for any kind of device behavior, device control system calls that any of the user VMs are going to make. So you need to know these things, right? So if memorization is the way to go to begin with, then that's how you will start. But at the end of the day, remember, it is all about applying. It's about having that knowledge and being able to put it in a different situation and be able to reason with what the use case is. That is what is important at this level, right? So keep an understanding of the Zen server architecture, or basically the Zen hypervisor, as we all know it, because it was one of the initial open source hypervisor architectures that was proposed by Cambridge, that eventually got adopted into a lot of the commercial variants that is out there in the market right now. So you need to have an understanding of that, right? You don't need to remember, examples of every different categories that are out there. You don't have to just, just say that, right? But to be able to explain, or if somebody tells you that, oh, this is what it is, and then you ask them the question like, okay, can you tell me a little bit more about it? When they give you that information, you should be able to relate to the fact that, okay, fundamentally, what does it relate back to? That is the important feature, right? And that's how interview should go. That's how your reasoning should go if you're working for somebody and you are responsible for setting up their cloud environment, right? So moving forward, at this point of time, of course, what we are equipped with in terms of our knowledge is basically the paradigm shift that we talked about, right? So in terms of the paradigm shift that we were discussing, there were two different spectrums of computing requirements, right? We talked about high throughput computing, we talked about high performance computing, and we will revisit this, but our ultimate goal is to close the loop. And I will tell you what I mean by that, right? So essentially, in high performance computing, supercomputers got replaced for the nodes of the network that was supporting high performance computing with commodity hardwares or everyday hardwares that was cheap, readily available, and that supported the idea of modular growth and scalability, right? So you had computer clusters essentially replace that. So we learned about the computer clusters, we learned about different design criteria, we learned about the issues and the challenges that are present in the computer cluster domain. And then different categorizations of computer clusters. We looked at the compute clusters that was there, the highly available clusters, the load balancing clusters and stuff like that. And then most importantly, one of the things that we learned, and we are going to revisit that in this current discussion that we will have today, is the single system image, or the SSI. Eventually that was replaced and implemented through the hypervisor itself, right? The software that implements the properties of the single system image design, right? In addition to that, on the high throughput end for data sharing and stuff like that, people came up with peer-to-peer networks, okay? And that was mostly for data sharing. Another important networking concept that came out of peer-to-peer is basically the concepts of overlay network. You might have heard this term before. If not, on a very high level, what it means is that if there is an underlying physical interconnection of physical computer nodes, on top of that, if there is a virtual layer of networking using which users essentially share their files and stuff like that, or reach out to a particular computer, then that virtual layer is known as an overlay layer. Because as the literal meaning of the name suggests, overlay, that's what it does, right? So remember, when we're talking about memory virtualization, right? We talked about the fact that there is a physical chunk of memory, right, on the actual hardwares itself. But what we see through our screens, it is directly not that physical memory, right? This file structure that we see here, right? On the left, you see all these desktop downloads, pictures, and stuff like that, right? This is a representation of your file system, right? But this is not, and this maps to the memory, but this is not actually, or you don't know where this is actually stored on this physical system. Makes sense, right? So when we are thinking in terms of memory, so you have a virtual layer on top of that, which essentially becomes your file system, and then you have your physical memory here, right? And we talked that there are address translation tables and then memory management unit, and this is what the user sees, the virtual part of it, right? So similarly for networking, you have that concept in peer-to-peer networks is that you don't essentially see the physical nodes itself, but what you see when you use a software in order to enter the peer-to-peer network, right? So you should be aware of things like BitTorrent. Again, it's just a software, it's not the piracy thing, right? It depends on what you share on top of it. There were things quite, 20 years back, there were things like LimeWare that was used quite popularly for music sharing before you had music streaming services like Spotify and stuff like that. Those were kind of the things. So when you enter this network using such a software, what you see is an overlay. You don't see exactly where the physical machines is. Nobody would want to expose that, right? Because physical machine in a way is a way to track where you are, geographically speaking, right? So anyways, when you merge these two things together, you can either create what is called a computational grid, or you can create a data grid if the purpose of the computer networks that is created is solely for the purpose of storing and sharing data, making data available, right? The modern day content delivery network, CDNs, that we are aware of, right? And we will learn about that when we look into database. But anyways, things kind of diverge from here, again, to give you an idea. So when Web 2.0 came into being, right now it's 3 and it's going towards 4.0. So don't worry about that. You had the modern day web services that we talked. So we looked into that REST API services, web services that came into the pictures and stuff like that. Then if you took virtualization, okay, we got cloud computing, but then we kind of supplemented this information with not just being virtualization, but things had to be dynamic. So we are also talking about elasticity. Okay. And then finally, here, if you applied sensing to this, okay, if the devices had sensing, then you got the Internet of Things infrastructure, and some people like to just simply call it cyber physical systems. We talked about the distinction between that, but some communities still don't accept that distinction, right? So it's a gray area. There is no like clear distinction between whether you should call it CPS or whether you should call it IoT. But that's not the scope of this course. If you want to learn more about this, you can actually register for 4160, at least for those who are undergrads. Okay, this is not a big. So anyways, so we talked about virtualization in the previous chapter. We have an understanding of what the design issues of computer clusters are, right? So essentially, when I say close the loop, is that this is like a, you know, non-cyclical tree or something like that, you can say. But what I'm trying to get at is we know that when this cloud computing offering becomes public, so that is Amazon that we know of, Azure, GCP, and stuff like that, we don't simply call it cloud computing anymore, right? The computing aspect that is there is known as service computing, okay? Or sometimes it is also known as utility computing. So basically, service computing and utility computing is enabled through cloud computing. Public cloud computing. You can have different variations of cloud computing. You can have a private cloud, which an organization themselves own, and only the employees of that organization can avail the services that that cloud provides, right? So it is not pay as you use, it's just you being a part of the company, you get to use that, similar to how you can use some of Oakland's services for being their student, right? But if you think in terms of your computing requirements, right? The original two computing requirements still holds strong. So that means if you are in the public domain and if you're computing as a cloud service provider, you still have to provide either high throughput computing or high performance computing, right? So how do we close the loop? So that means how do I basically tie the public cloud offerings or service offerings, right? Public cloud computing offerings back to HPC and HTC, going through all of this evolution to the current day offerings that we are familiar with, right? So we have bits and pieces of the structure right now. So we know that what the physical infrastructure should be consisting of, right? It should be computational or data grids. We know that pretty good, right? But we know that that is not going to be using the resources that are fully available to us. We need to boost the concept of resource sharing and resource utilization. Cool. So we learned about virtualization itself, and that furthers our resource sharing capabilities, either through multiplexing or breaking down of that software and then divvying it up amongst all the different users that are there, right? So now there are a few more concepts that are still left for us to learn, right? How do we consolidate this into a server technology, right? So we can provide the service, so to speak, right? And then how do we make this dynamic in nature? Because we talked about this is one of the key aspects of making sure that cloud is what cloud is supposed to be, is not just through virtualization, but through elasticity. And elasticity is another way of saying that things should be dynamic or on demand, right? So it can dynamically scale up if the user's requirement or demand goes up, or it can dynamically scale down when the user's requests or demands go down by itself. Because remember, when we started virtualization, or we started the primary motivation behind cloud computing, it was to shift the responsibility of owning and maintaining your hardwares to a third party. Does that make sense? Always remember that, right? So if you shift the owning, of course, forget about the ownership entity for a second. Let's say somehow you were able to procure it, right? If they are maintaining it, they need to maintain your user base's demands as well, right? So you are not responsible for just sitting there and then monitoring like, oh, in Black Friday, my user request on my website just went up tenfold. You cannot wake up in the night and sometime, 2 in the morning, you get a call, it's like your server crashed. There goes your business, bye-bye. Then you will not go to that person anymore, right? In order to host your application and stuff like that. So whoever is responsible for making sure that this is up and running, they need to first focus on, not first, but eventually focus on elasticity. That is dynamic allocation of resources. So that is basically the focus of this discussion, which is virtual clusters, is how through virtual clusters, essentially by transforming computer clusters using virtualization, do we enable elasticity? Once we have that piece, we basically have the fundamental pieces of your puzzle or Lego, whatever you want to call it, to essentially moving towards building your own cloud computing architecture. Does that make sense? Right? And one of the key features within virtual clusters that enables the actual enabling technology behind elasticity is the concept of VM, virtual machine, live migration. So that is one of the keyest concepts, and that is the major takeaway of this chapter that we are going to learn is what is virtual live migration, not virtual live migration, but virtual machines live migration. Okay, how do you do it? What are the different techniques that are available to you, right? What are some of the do's and don'ts that you have to keep in mind when you're performing virtual live migration, virtual machines live migration, right? And essentially how that helps us to close the loop that we are talking about. How does that get us to having a cloud computing platform that supports high throughput computing and high performance computing on a service model that is pay as you use model, right? So that is what I essentially am trying to imply when I say close the loop, right? So with that in mind, let's start with the architecture of our virtual clusters, right? Straightforward, there isn't any complications here. If you're creating, so again, to keep in mind of the different topics that we are going to discuss, what is this? Okay, so we will talk about how to perform virtual machines live migration, understand what it is. One of the most bottleneck problems that you will face when you are performing virtual machines live migration is how to migrate the memory and the file system. Because there is no complications when it comes to migrating the CPU, right? And there is no complication about connecting it with the IO devices because somewhere, wherever you will take it, right, it is kind of assumed that IO devices might be available. So the only thing that remains is how do you migrate the memory? And memory is one of the major bottlenecks in architecture. Okay, CPU chip technology, the advancement that we have seen in the last 25 years has been quite manifolds compared to the advancements in storage technology. So, right, if you have taken a course in comp architecture, if you remember it, one of the major times that it takes is the disk seek time. Right, so if you need to look for something in your actual hard disk drive, bring it into your main memory, right? That is the most time that you will spend in executing something. So it is always said to reduce that time, right? Don't have to switch and bring things into the main memory multiple times, keep it minimum, right? So that's basically the discussion that we will have here. And finally, if we understand what is VM live migration and how to address the bottlenecks of memory and file migration, we will get an understanding of the dynamic deployment of virtual clusters, which essentially is what the foundation of elasticity is all about, the dynamic aspect. Okay, so these are the topics of interest that we are going to look into. So what is the architecture of a virtual clusters? Pretty straightforward. As virtualization suggests that you are dividing the available physical resources amongst multiple isolated containers. Well, not containers in the actual formal term of containers, but isolated environment or boxes within which you can run multiple containers. That's the VM. So if you take it a step further and ask yourself, what is a virtual cluster? Well, basically, if your underlying physical resource is a computer cluster, right? And you can have multiple of those computer clusters connected over the Ethernet, okay? And then you apply the concept of virtualization technology on top of that, what it yields is basically a virtual clusters, okay? So now the thing about virtual clusters is it further improves the resource utilization of your typical computer clusters. That's kind of like a no-brainer because that is the primary motivation behind virtualization itself, right? So, for example, what we're seeing here on this particular slide is that let's say if you have 3 physical clusters, and you can assume how many number of actual physical nodes that you may have. So what you can do is you can create clusters, virtual clusters, using these 3 physical clusters. And the main important thing that you have to keep in mind, that few features that you have to keep in mind, is that when you create a virtual clusters, the VMs don't need to be a part of the same physical cluster. So what that means is, let's say if you have physical cluster 1, how many virtual clusters do you see here? Or how many virtual nodes do you see on top of that? So you have 1, 2, 3, 4, 5, 5 here connected through a communication bus, right? Could be an Ethernet. So you have 10 nodes total that is virtualized on top of this physical machine, physical cluster. And you can assume how many nodes there are, preferably less than 10. Otherwise, you're not boosting the resource utilization per se. You can always claim that there is 10 physical nodes and 10 virtual VMs that you have created on that. But remember that results in a scenario that is quite well known in cloud computing as well. It gives you a dedicated node. Okay, essentially later on when we discuss about the type of nodes that is available on AWS, and as a result, it's also available on Microsoft, Google as well. But there is actually a particular offering, a service provider that is known as Rackspace. Okay, essentially, as the name suggests, you rent out a space in the rack itself. So you are actually taking dedicated space and running your application there, right? So there are options of renting and leasing over an extended period of time that reduces your pay-as-you-use cost model, right? So essentially, if you say this, it's a 10 on 10 for this particular example, that there's 10 physical nodes, and on top of that, you have a single VM that is running. You can say to a certain degree, it is synonymous to having your own physical machine. Okay, but we are not talking about that specifically. John?
Yeah, just wondering, do you consider a virtual machine in a cluster a redeployable thing to another cluster? Would that be a concept?
So say that again.
Each virtual cluster has a VM, right?
Each virtual cluster as a VM, can you take that to another physical cluster?
No, to another virtual cluster.
To another virtual cluster. So let us take an example and say you want to take the entirety of virtual cluster 2 and put it inside cluster 4. Is that
some of the VM inside a cluster or all of it? I mean, I'm just wondering the redeployability of the architecture.
Yes.
Okay.
Yes, you can do that as long as there is something here to create further nodes where you will basically take each of these and migrate it.
Okay.
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 All right. Where were we? All right. So let us just assume here that the number of physical nodes is K, right? Each machine of that K devices are pretty strong in nature. Let us just assume that for the sake of discussion. So you can say they have 64 gigs of RAM. They have like, terabytes of storage. They have good CPU power and stuff like that, above 3.2 and things like that. Let us just assume that, just for the sake of discussion, right? And we can also assume that K is less than 10, okay, for now. Or maybe you can go more than 10. Right now, what we're seeing is just an example. You can go above, let's say, the maximum threshold capacity is around 100. And then we can just say K is much, much less than 100. Let's just say that. So what this architecture tells us, that is when you're creating these virtualized clusters, right? Your virtual clusters need not have node that has been virtualized over the same physical cluster. Again, I repeat, when you create virtual clusters, the nodes of that cluster need not be virtualized over the same physical cluster. So that means I am not restricted to creating a virtual cluster which will consist of VM which are physically running on the same physical cluster, on different nodes that belongs to that same physical cluster. Does everybody understand this? So case in point, I have virtual cluster 1 here, 2 here, 3, and 4. Notice the participating nodes of virtual cluster 1. You have some VMs which has been virtualized over physical cluster 1, some VMs physical cluster 2, and some VM over physical cluster 3. So this is what I mean, that the participating nodes of a virtual cluster need not be virtualized over the same physical cluster. It can be from multiple physical clusters, right? And this is what enables, or this is where you start getting into the features of transparency, because as a user, you will be interacting with your cluster, right? But you don't know on top of which physical nodes have these VMs been created over, right? Here you can say that, okay, virtual cluster 2 belongs with nodes, and we can see this because of the architecture in front of us. They all belong to the physical machine, or they're all deployed on top of the physical cluster 3, right? Similarly, for virtual cluster 3, all the nodes have been created over physical cluster 1. Same goes for 4, right? But you need to remember the two features is, the first feature is, for any virtual cluster that you create, the node need not belong to the same physical cluster. It can belong from multiple physical clusters. That's the first feature that you need to keep in mind. The second feature is, your virtual cluster need not be just composed of virtual machines. It could be a combination of virtual machines and actual physical machines, just in the virtual clusters, right? This design criteria will evolve eventually, and everything will be physical in nature, right? But think of it this way, is that when I say that your virtual clusters can be a composition of VMs as well as actual physical machines, do you think people will give physical machines, like service providers will actually make it a combination of physical and virtual machines? Or will it be some different notion of physical machines which replicates the behavior of a physical machine? Does everybody follow what I'm trying to ask here? Yeah. So two features, right? So the first feature is clear, that the nodes may belong to different physical clusters, but it could be a part of the same virtual cluster. All right, all good. Second thing is that your virtual clusters could be a combination of virtual nodes or physical nodes or physical nodes. So that is clear, is understandable. But when we say that physical nodes can be present, do you think actual physical machines are a part with virtual machines to make up that virtual cluster? The answer is no, right? But then how do you mimic the behavior of a physical machine? What does it mean to have a physical machine in this particular case? How can you create a VM that will mimic the behavior of a full physical machine? Think about it for a second. What is the concept of a virtualized environment? Or if you take, let's say this is your, let me do something fancy. I'm tired of this. Yeah, this is cool. All right, so let's say this is your hardware, right? This is the hardware. When you think of, and you have, type 1 bare metal architecture, microkernel, blah, 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 everything. All right, so you have your hypervisor here. Okay, on top of this, when you create VMs, what does it look like? Like this, right? So you have VM1, VM2, VM3. What are they doing? What does creating virtualization do? It boosts resource utilization through resource sharing. That's the whole idea, right? So that means for a limited amount of underlying hardware capacity that is available, I am boosting its utilization by sharing it amongst multiple users. Let's say U1, U2, ... UK, where K is some number bounded by a capital N, whatever, right? It's not an algorithm. So anyways, so you get that idea. But how do you share the resources? What is the conceptual technology that enables you to share the resources? This is important, and please remember this, right? Write it down somewhere. This is one of the core concepts on which cloud computing runs, is the concept of multi-tenancy. Okay, and this is losing its charm. Okay, so again, this is one of the key concepts that allows you to enable resource sharing, multi-tenancy, right? What is a tenant in English? Tenant is somebody who rents something from you and maybe lives in your apartment that you're renting out and stuff like that, right? So when you have multi-tenant, what does that mean? There is multiple renter for your apartment itself, right? So the way you enable this multi-tenancy is through this concept of multiplexing. That is switching between the available resources between multiple people when they are not using it, right? Of course, when you're using it, you cannot just kick them out. Actually, you can, but we will talk about that later. That is only when you use the free stuff, right? You have the option of being kicked out. AWS actually has that, but happens very less frequently, but still is there. Anyways, without digressing there. But now, if you understand this, coming back to our original question, how can I make this environment seem as if it's a single physical machine, but still have virtualization? What do I need to do? What do I need to suppress? Is the question clear? It actually looks pretty bad on screen. What do you need to do? If I want to convert this diagram that you see in front of you, which is basically a concept of multi-tenancy, that is, you have multiple tenants sharing the underlying resources that is available amongst each other through switching of resources, right? Multiplexing and stuff like that. If I want to convert this behavior, transform this behavior and make it perform as if it was a single physical machine that is being used by a single user, what do I need to change? What do I need to suppress?
Don't you need to hide the changes done on other VMs? I mean, you want one VM to think it's the only one.
No hiding. No hiding. Hiding. It's still hidden. When you implement VMs, there is isolation there.
Yeah.
But I want this whole architecture, what you are seeing right now, to behave as if one user is using a single physical machine. See, right now, this machine that I'm instructing with, it's a single machine and a single user is using it. And so I can say there is no virtualization here. I'm using a physical machine. You guys are thinking too much. Simplify your thought process. Yes.
Maybe like compartmentalization, putting them in different compartments.
No. Simplify your thinking. You are overthinking right now. If an apartment has multiple tenants, but you need to minimize the apartment so that only one tenant lives there, what do you need to suppress? The concept of multi-tenancy. If you have multiple tenants and you need to bring it down to one, what do you need to suppress?
Accept only one tenant.
Only one. That's what I'm saying. You guys are overthinking. We just express the concept that this is enabled through multi-tenancy. And when you have multi-tenancy, please keep in mind that there is already isolation that is there, right? So that one VM does not interfere within the process of another VM. This is one of the attacks that can happen on cloud computing as well. Okay. So all I need to do is to convert this behavior to make it seem as if a user is using a single physical machine. I need to dedicate this entire underlying resource to a single VM, and that's it, right? So whoever that VM user is, they will use the entirety of that underlying hardware that is available. And that is the concept of dedicated places on cloud computing. Yes.
That example, the different VMs to partition off.
Yes.
So you're just trying to, in this case, convince the user that there is no partition. They have access to the entire VM.
So typically, when this is enabled, right, a single underlying resource is supporting multiple VMs, but each VM thinks that they are the only ones who are operating on that. That's your question, right?
Oh, yeah. Right now, one doesn't know that you choose.
No, it doesn't know, right? But still there will be interference in the form of, because there is limited resource that is there, right? So you have to switch between the resources whenever one system call is made from one VM compared to another VM, and the hypervisor got to manage all, right?
But you convince the user that
you don't. The user pays for it, so you give them the dedicated space. So there are availability there. So right, if the user comes and say, I want a dedicated space, but there is no multi-tenancy, So first of all, I'm suppressing all the issues of vulnerabilities that can come from any other user, but I also want unrestricted reservation of the underlying resources.
And you just charge that tenant.
Yeah, you charge that tenant more, and typically tenants like this, they rent it long term. They don't rent it hourly like
Contract.
retail users do and stuff like that. Yes, contract based. Okay, so when I say for this second feature here, that it could be a combination of physical and virtual clusters, then remember you don't necessarily add the physical cluster, the physical node itself. Because what is going to be the problem of that? If I take this entire computer and take it and put it apart as a virtual clusters, you're going to face an issue with respect to scalability. Because what happens eventually when that physical node itself runs out of, space? You need to add something to it, the modular. So you cannot just go to the market, buy another computer, laptop, bring it again, and then connect it, right? That doesn't sound a reasonable way of managing your business. Okay, so you still virtualize, maybe resources are available, but you have to figure out how do you have to do it. Yes.
This node which what we are referring to with this node, it can be VM or it can be physical cluster.
It's a VM.
So
The node itself is a
each box
VM.
is a node, basically.
Louder.
Each box is a node.
Each box is a node, a VM. This you're asking?
Yes.
It's a VM that has been virtualized over the actual physical machines.
Then what is node?
Then what is?
Node. What do you mean by node?
These are the nodes.
So each VM is a node. basically.
Yes. Okay, so these two features just keep in mind when you're working with virtual clusters. Okay, that is the important thing. All right. So again, just to recap everything that we discussed and a little bit more that might have messed from the top of my head is the provisioning is done dynamically. So the basis of creating the virtual clusters is to allow you to make sure that these nodes that you saw can be created on demand.
Can you go back to that
Back to this.
previous slide?
Yes.
So when a request comes from outside, which node it will go to, how do you know? Because it is a cluster for external system, it is just one machine, maybe or one system. So how it will decide which VM will serve that request?
So there is another software. So what does a hypervisor do? So a hypervisor is responsible for managing and allocating resources on a single physical machine, right? There is something that is called a Vim, not the bar that cleans. But essentially what it stands for, and we will learn about this a little bit later, is it's called a virtual infrastructure manager. VIM, virtual infrastructure manager, which kind of behaves similar to a hypervisor, but for the entire cluster scenario. So now when you set things, or when you, to answer your question, is like a user comes and a user makes a request. Why does it say to write? When a user makes a request, okay, typically in the cloud computing environment, the user has to select, the user maybe is an admin of a company or something like that, right? It is divided based on availability regions, and then it is further divided based on availability zones. Inside of these availability zones, you have what is known as data centers. Inside of data centers, then you have these virtual clusters supported by storage. And when I say storage, I don't mean hard disk drive. When I say storage, I mean full-fledged DB servers, which in itself are virtualized. Okay, so now when the user comes and makes a request, and the virtual infrastructure manager is basically residing here. So this is like a trickle-down effect, right? So the user tells me or comes to, and based on the interface, they select the availability region. Let's say I select North America, okay, NA. And then you will have multiple availability zones. So then the user will see there is one in Seattle, there is one in Cali, Northern Cali, there is one in Ohio, there is one in Virginia. Okay, unless they have opened one more. I don't know if Texas is open or that's just a supporting edge center. But anyways, so you see these options of availability zones, right? And let's say I select Ohio because I am in Detroit, right? So that pinpoints, and so that sends a request to the VIM for the data centers that are managing Ohio. And then the VIM allocates the nodes or either instantiates the nodes and then allocates the user request on top of those nodes.
But this cluster should be available in different zones also, right?
Yeah, you can replicate that. Yes. If you
So
want to
for an
replicate that.
external user who is using let's say I have a website which is available in different, maybe different regions.
Mhm.
So I have created a virtual cluster which is from different data
Re-
centers.
Yeah, sure.
Then if a request is coming, how it will decide which server should serve my request?
Also, you're saying all the servers that are across, so the multi-AZ that is called, that you just described, the multi-availability zone deployment. So all of them are active, right?
Yeah.
You will serve it where your latency is the lowest. If you're thinking in network latency, how do you decide network latency?
So, but my request, how it will decide where to go?
Your requests don't decide. There is a load balancer that decides based on your closeness that how much latency will it take. So let's say you're running a server.
Basically, it will receive all the requests and it will decide internally where the request.
Correct. Exactly. Right. Because yeah, so if I have one running in Ohio, let's say, and if I have one running in, let's say, Tokyo, let's go out of North America itself, right? So if a request comes from Detroit, right, it will first hit what is known as a front-facing load balancer. The load balancer determines where, based on the available virtual cluster of servers that are running, should this request be redirected to in order to minimize the latency, and as a result of that, ensure that the quality of service stays intact, right? And then it sends it to the nearest available region. Okay. Even on top of that, just to take your architecture a little bit further, you just don't have right now in this current day and age the capabilities of multi-AZ deployment, but you can further support this with edge networks. So for example, there might not be data centers that are available in itself, right? But there are edge servers that are available that can further reduce the latency. So last I checked, this was a year ago. I haven't yet checked it yet. So Texas has an edge center. I don't know if they have made that into an AZ or not. But essentially, if they're so where Texas falls is that the nearest is where? Virginia, right? Or you can take it to Cali. There is one in Northern Cali and stuff like that. But if you have something that is closer to Texas itself, then all the Texas user requests will be served through them. Right? So you can, improve your architecture based on that. Okay. But that answers your question? Okay. All right. So again, dynamic deployment, that is one of the key factors that you have to keep in mind. The node of a virtual cluster can be a physical machine or a VM itself, but know that you don't want to take an actual physical machine and connect it, because then you will essentially hit a problem with scalability eventually, right? Because I'll tell you a funny story. If you think deeply, right, when we say physical machine and you think of the brute force solution, you're actually going back. You're not actually going forward, because if I say that if you take a physical machine, connect it to your network, right, you will hit a problem of scalability. That is pretty true. Yes, no problem with that. But then you will say that, oh, then I can bring a physical machine which has a lot of power, right? If you keep increasing the power, what does that physical machine become? Eventually, it loses its categorization of a commodity hardware readily available and cheap, and you go towards having a supercomputer. That is going back to the 70s, the 60s, where you had a supercomputer supporting your computations, right? And you cannot replace the supercomputer that easily, right? So that is something that you want to keep in mind. All right. Always remember that the VM runs what is known as a guest operating system, and that typically will be different from a host operating system if it is present. The reason why we say if is because it depends on what type of architecture of hypervisor are you implementing, type 1 or type 2. Because if it is type 2, there will be a host operating system. If there is a hosted hypervisor, there will be a host operating system. If it is type 1, there is no underlying host operating system. Keep that in mind, right? So those are the things that you have to keep in mind. And then when you develop virtual clusters, you can improve application flexibility. And we will talk about that in the slides that are upcoming, right? You can also replicate the VMs to create what is known as colonies of your clusters. And that replication will further boost the features of distributed parallelism. It will increase fault tolerance. And if fault tolerance is increased, it will also increase the concepts of recovery in case of a crash, right? This should be easy enough to understand? Does anybody need an explanation on this? All good? Everybody understands this? Okay. All right. And what is important is when you build virtual clusters, that is when you start making things elastic. Okay, just like Sia said, you might stretch it too hard, but it will come back. That's maybe not the song, but you get the idea, right? You can stretch it. That's the point, and it will come back. That's the point, right? It's a bad joke. Anyways, and the last thing you have to keep in mind that if a physical node fails, all the VMs on top of it will fail. That is the reason why you require this colonization behavior. Okay. However, if a VM fails, that does not mean the physical machine has failed. Right? This is an interesting concept that you have to keep in mind, which kind of brings me to my next question. Has anybody seen the series Colony? Has anybody seen the TV series called Colony?
Colony?
Yeah.
Colony, I didn't finish. I did 2 seasons, so
How is it?
that's why I stopped. So I lost interest.
Is season 1 worth it though?
It was interesting, so that's why I went to season 2. So
Okay. So I'm still debating that. So if somebody wants to, take the fall for me, watch it and let me know. That would be quite a preview. But anyways, don't have the time for that. Anyways, so other things that you need to know is that, of course, just like virtualization enables virtual cluster itself, since it is supported by virtualization, you have application partitioning and user customization. Okay, and we'll talk about that. But what matters the most when you're creating these virtual clusters, and that brings us to elasticity itself, is it's not about the creation of the cluster itself or where you put it, but what is more important is these virtual images that are used to boot and instantiate all of these different nodes in your virtual cluster. How are you going to store them efficiently? All the problem is with storage. If you go forward and you boil it down, because we talked about this previously as well, right? If you create, let's say you and I are a user, you come to these virtual clusters provided as a service by somebody, right? I choose a Windows machine, you choose a Windows machine. I choose Windows 11, you choose Windows 11, right? I have a basic set of an application stack, which is quite similar to yours with the exception of, let's say, 1 or 2 applications. So what happens now if you extend this scale, right, and make it like thousands, 10,000s of user with quite similar, computational requests, you will end up with these disk images for your VMs that will have a lot of redundancy and overlap. Right? So you don't, the brute force way to save all of this is like you save the instant or the image for each and every user that is there on your platform, right? You don't want to do that. It sounds, quite less intuitive, okay? But that is the brute force way. So you need a better, more efficient way to store all these disk images and the profile that comes with it. The profile, when I say, what I mean is the application stack that needs to go with the VM images. Because remember, booting takes time. Okay, so you don't want to boot from scratch every time a new user comes, because that is going to put a dent in your policy of dynamic allocation. Or you are doing things dynamically, but it takes 1 day to boot up. Well, it will not take 1 day, but it will take a considerable amount of time to boot up, right? And you know how the users in this day and age are, because of all these 30 seconds videos and stuff like that. Everybody has lost their patience, right? So everything needs to happen immediately, right? So nobody has that time, just like that meme, and nobody got time for that, right? So there has to be a efficient way, and the efficient way to do that is what we call as creating templates. Right, and the time when we go to Amazon AWS and we start to instantiate our VMs, learn how to do that when we are using the Amazon EC2. Okay, EC2 stands for Elastic Compute Cloud, right? That's the 2 C's: compute cloud and elastic part of it, right? So they've given in the name itself, it is elastic. If you stretch it too much, it will come back and hit you. That's not true, by the way. Okay, don't take it on my word. Anyways, So basically, when you instantiate this, what we are given as a choice, as an option, is to create our own template. That is, they give you the template that they have already stored. And what they do is they take all of these templates and they put it across all of these different clusters that you can create, by the way. So that there is no time that is spent, there is no downtime that is spent in order to create new templates, right? So they create all possible structures that they can, leave the rest up to the user. So that is the reason why there was this concept of user customization here. What will the user customize? Well, user will customize basically based on the additional application, which is not part of the default template that the cloud service providers have created. So they put it as user data. So when we go to AWS, we will see this again, but just to give you an idea, there is a form, like it's kind of like a form, right? Where you get to choose a lot of the default options, like how much CPU do you need, how much memory, what is the RAM capacity, processing power, what type of OS image do you need, blah, blah, blah. At the very end, when we come down, there is this section, this text area called user data. Okay. And essentially what this user data is for you to write down scripts that will install different type of applications that is specific to you. That is what user customization essentially means. So let's say you need an Apache to support a PHP and you don't see that in the template. Of course, it's a quite common template, but let's just assume, just to understand this, is that it's not there, right? So what you do is basically you write all the commands, the terminal commands that is essential in order to install Apache, in order to install PHP and any kind of editor environment that you need, and just write there in the user data section. And then when you launch the VM, what AWS is going to do is it will take all of its predefined elements or fields that you have essentially interacted with. But in addition to that, once that VM is instantiated, they will automatically, okay, install all of these commands that you have specified. And that will create your own application stack in addition to the default platforms or default application libraries that is present in that environment, right? So what does this allow? Yes.
Like would also include the OS to be defined.
Yes, the image that you need to use.
So how would you know, like in advance, how many of each OS would you like install on the node?
You don't, you choose the number of instances of that particular image.
So you're just basically guessing, like anticipating what the user.
Oh, so you're saying from a user's perspective, how would I know how many do I need?
No, like from the provider's perspective, like how do you know how many windows do I put like nodes within these virtual clusters?
You don't. So the user tells you that I need these many machines of Linux distribution and these many machines of Windows distribution. And then there is also an option to specify dynamic allocation, that if, let's say, my CPU utilization for, let's say, the 5 initial deployment VMs that I'm asking for goes above, let's say, X percentage, then you add one more, right?
You're not really pre-installing that until like you would be pre-installing before the user would. Like,
No, not before. No. So it's not prediction. There is no prediction involved. That will be kind of interesting if you can do that. But that's not what happens. Somebody comes, tells you your initial requirements, you set up the environment, and then there is a clause of how you're going to manage the dynamic aspect of it by certain condition and thresholds, which are monitored by certain softwares that are running on top of the virtual clusters, right? So it checks the heartbeat and stuff like that. So if a virtual machine fails, it will bring up another one, right, in order to replace that. Or if the usage behavior changes and the user specifies what is their desired usage behavior. So if it goes above that, they will probably deploy a new VM to balance things out. If it goes below a certain point, they will shut down an existing VM. Right? So it might even result in a scenario where I come and say, oh, I need 5 VMs. And each of these 5 VMs, make sure that the minimum capacity does not go below 20%. And let's say it goes below 20% in one of the VMs. So even from that initial requested, cloud will shut down that 5th VM because it is below 20%. And you will have 4 running. So that's the dynamic aspect. But it's not predicted. The cloud will not know what you need. You need to start off with something. But the thing is, when you say that I need a Windows or I need a Linux or I need a Mac, right? Then the cloud has that ready. So that is what we mean in terms of managing the VM images more efficiently. Like instead of waiting till the user telling us that they need this kind of distribution, we create that and keep it ready. And we create some level of, different choices for the user. So 1 gig RAM, 2 gig RAM, 3 gig RAM. So essentially, we'll talk about it, but what you can do is you can select one of the most simplest kind of structure is known as a T2 micro. So that is a profile. That profile comes with how many gigabytes of RAM, how many CPU cores that you need and stuff like that. So that is already different. But the user comes and tells how many of that they need, right? And then we just deploy that number. Okay. So this enables fast deployment and effective scheduling, one of the important things in order to manage dynamic aspect of behaviors, right? So some part of the software stack, which is essentially going to be OS, it's going to be library or the different types of apps. So like you need a browser, right? Then it will be deployed there, right? You need a development environment in order to code and stuff like that. So that will be deployed there. So you can specify all those information, right? OS is a no-brainer. I'm not explaining why you need an OS in a software stack, but everybody gets that idea. So it's understandable. But the other thing that is supporting fast deployment and effective scheduling is to be able to quickly switch between the environments of one user to another user, right? That is the multiplexing aspect of it that supports multi-tenancy, right? So, yes.
We can store our own image as well.
Yes, you can store your own images.
AWS provide that kind of facility.
Yes.
Like you create my image and it will be.
You can upload that, right? So there is a Amazon marketplace for images itself. So you can create your own image and submit it. They will check it. Once it passes the initial check to make sure that you're not trying to do anything weird or malicious, then you can essentially have other users use your image as well if you allow the permission. Okay, so there is a virtual image marketplace itself where they have different users have come up with their own stack and they think, oh, if somebody else needs it, then they can essentially use it. Okay, so you can either choose Amazon's own images that they have created, or you can go to this marketplace and use these public images. Okay, but if you submit an image, it takes a little bit of time, a good time to go through that check. It's just like submitting an app on the App Store or something like that, right? You won't freely be able to use it. You need to first make it sure that you're not running any kind of malicious commands that will bypass cloud security.
Banks may not allow any kind of images to be used. They might be having their own image maybe because of security.
Yeah, of course. Yeah, you can do that. But in such a situation for fintech, specifically speaking, right, they might not even share it. Right. But I'm saying from a public perspective, you can do that as well. All right. Just to keep in mind. So the ultimate goal is to improve the storage, right? So you need to, like, if you are a cloud provider, you need to basically procure hardware that will improve the optimization of your storage resources, right? And you need to minimize the overlap. Even if you think of templates that minimizes a little bit of the overlap that we talked about, overlap can still be present, right? So you need to use techniques that reduces or removes unnecessary redundancies. Please take note of the word unnecessary because sometimes redundancy is helpful as well, right? So in order to reduce that, some of the techniques that are available is basically you can perform hashing. Okay, hashing, the hash that you create for a content allows you to compare different contents and see if it is completely similar or not. Okay, so if you do that, then you can perform hashing on the storage values and you can check if it is completely similar, then you can essentially remove that, right? So things to keep in mind. So how do you deploy these group of VMs? Of course, the number is something that you can specify, but the first thing is you need the image. You need the guest operating system, right? So that is what we call an image. Remember this interchangeably as we keep moving forward, we would stop using the word host operating systems eventually, and we will just call it images. Okay, so keep that in mind. All right. So the other thing is when we say images, moving even forward, we will eventually stop calling it images and we will just say what template are you using? Because the template captures your specifications itself. Right? So when we say we buy a computer or a phone right now, we say, well, what are the basic specs? Right? And this somebody says, you know, it's using this chipset, this processor, this much RAM, this much memory, blah, blah. Right? On cloud, if you decide that this is going to be your path, you need to be familiar with the templates. and know what the template maps to in your head. That will come from practice and experience. Nobody expects you to know from the get-go, but some of the basics you need to know. So for example, if I tell you you have a T2 micro, what does that mean? Right? So when you become proficient in this domain, this is what you need to know. That if somebody tells you the profile, what does it map to? Right? There are some of them that are kind of optimized for memory. They start with M's, and then you have larger quantities, essentially making it map to larger spec values. Okay. For now, you don't have to memorize this. There is no need for it, but you need to remember that essentially the guest OS is basically the disk image, right? And every image will have a certain level of allocation in terms of CPU, memory, and all of those jazz, right? So that is basically mapped into templates.
So the naming is like universal, it's not based like on the provider, they don't.
It's not universal, I would say. I don't exactly know from the top of my head how Google and Azure names it.
It's a little different.
It's a little different, but it's the specification mapping that actually that matters. So even if you, let's say, work with AWS for 3 years and then you move to something that requires Azure or something like that, as long as you understand the specification breakdown, you will find the naming convention that is used for the other provider. That is what is more important. Yes.
When you say M2 is optimized for memory, what does that mean in terms of specific? I mean, it's just more
So-
memory, different type of chipset to optimize
No, no,
memory.
no.
I mean, what do you mean by
So
that?
remember when we talked about computer clusters, right? And the classification of clusters, there were some which were optimized for computing itself, that is high performance computations. Then there was something that was for high availability and stuff like that. So that based on that, they're creating these profile categorizations. So there is one that is with G. That's for GPU, right? So those are kind of optimized to support, let's say, image-based machine learning applications and stuff like that, which needs GPU capability, right? So this is the high-level stuff. I will dive a little bit deeper and give you a more accurate explanation of what makes it different, right? And I'll let you know that when we get to that, okay? All right. And then you have to configure your VMs, right? You select your profile, and then you still get the option to attach more storage, network settings, how much CPU cores do you need, and stuff like that. And then you can add your own information to it. We talked about that script at the very end of the template before you create it. If you want to add your own software stack that is not a part of the initial profile that you're selecting, then you can go with that, right? After that, you need to select the destination nodes. Destination nodes basically means which availability region are you going for, which availability zone are you going to select. That is what the destination node is. You don't, as a user, get to select exactly which physical machine is going to have your VMs. That is beyond you, but you can point to the group of data centers where it will be sent to, right? So that is the only option that you get. You get to pick on two things: the AR, the availability region, and the availability zones within that availability region, right? After that, you don't get to pick, okay? Because of course, for transparency purposes and stuff like that. So once everything is done, you just execute it. There's a button at the end, which is like a submit button of a form. And once that is executed, it will take all of these, essentially this information that you have provided, interacted with its portal, and then it will be deployed to one of the data center or the physical cluster nodes, and it will be created in the form of a VM, right? Just to give you what is the opposite of hindsight? Foresight. Okay. And I forgot what I was going to say because of this. All right. So what happens is when you create your own virtual clusters, by the way, right? Every time you go to a public cloud service provider like AWS, Azure, right? You create what is known as a VPS. Not a virtual private system that we learned in virtualization, but this is known as a virtual private sub. This belongs to you, right? You as a user, right? Everybody has their own virtual cluster. That is an important thing to know. Within the virtual private server, there are two types of clusters that you can create, right? One is a public cluster and one is a private cluster. Within each of these, you can deploy a node or multiple of nodes. So I'll just say not singular, but plural. It will be kind of counterintuitive if you just put a single node. And then there will be networking between these nodes within these public or private clusters that is a part of your virtual private server itself. Right? So now, what makes a cluster public and what makes it private? Can you reason to me based on object-oriented programming? That is something that everybody is familiar with, right? OOP, Java, OOP. What makes something private? What makes something public? Can you give me that core distinctive criteria of, if I ask you this question? Yes.
Accessibility.
From, you cannot just say accessibility, you have to specify from. From where?
Outside.
That's pretty good. Perfect. Now apply it here and tell me what does outside mean here in this scenario. What is outside?
Outside the VPS.
Which is what? What is outside? What are the two different? No,
Availability zones.
no,
From internet.
yes. Outside, public, in this environment is what? Internet. What are the two different types of communications that you have in computer clusters?
Enclosed.
Enclosed and
Exposed.
exposed, right? The exposed part is basically the connection from the internet. Internet is the public domain, right? So here, when you have, and how do you connect to the internet? Does anybody know this?
There's a series of routers.
Yeah, DNS and all. Domain namespace is a different beast.
TCP/IP.
It's address, right?
TCP/IP.
TCP/IP, that's the protocol itself, but the device is
A series of routers.
a series of router, and the final router is called a. Aha. That's the best part. It is right. Gateway. Right? That's the final router. A gateway device is essentially a router, but it acts as a bridge between two networks. Right? So what happens is the public cluster that you have, the public virtual cluster, will have a gateway device that allows you to communicate with the internet. So now if I ask you, and that question perfectly answered. So if I put it this way now, in this domain, how do you distinguish between a public and a private cluster? Again, I'm just saying cluster, but remember everything is virtual here. We are no longer in the physical. So accessibility, yes. Accessibility to the internet, that is what makes one public versus makes one private. So that means in a private cluster, what you don't have in terms of infrastructure, what is absent?
Gateway.
A gateway router.
Yeah.
Right? That is essentially what it boils down to. Now see how you developed, how you brought this from something that you knew, which is completely unrelated to this, but it's still related. Right? So when I say, when you are preparing yourself, you don't need to memorize it, you need to understand and apply. That is important. So you can take what you already know and try to reason with something that is there. Because these things did not just fall from the sky, even though it is cloud computing. Haha, see what I did there? Right? Even I am amazed at myself. But anyways, so you need to know this is built on top of something, and that is what we are spending time in understanding. It's like, how does the connections happen, right? So that you remember longer. Anyways, but a thing to note is, again, go back again. So how do you discuss or how do you reach out to anything that is private in OOP? Come on. Let's say I declared a few data members private. How do I access them?
Structure.
Which is what?
Getters and setters,
Getters and setters, which generally needs to be
public.
public. So public data member functions allows us to access anything that is private.
Encapsulated. Yeah.
Right? So that means if you want to reach out to this, how would the routing happen? It has to go through this person, right? So that means the only space that can access anything that is a private cluster within your VPS is your public cluster. See how they took OOP and brought it here? So now once you realize that, it doesn't seem that convoluted anymore. Things starts to simplify itself. Anyways, coming back. All right, so execute it. Now, what is important in this whole area in order to support that concept? So we said that there has to be elasticity. That was our primary motivation based on which we started our discussion. Elasticity enables the dynamic aspect. All right. And none of this will be possible unless live VM migration is supported. You cannot make things elastic. You cannot make things dynamic and on demand if you do not support the concept of live VM migration. Okay. Everybody can do offline VM migration. All you have to do is shut down your service. But that is going to cost your reputation, right? Because your service is down every now and then when you have to scale up or scale down. Nobody wants to do that, right? So that is the concept of live. That's where the live part is coming from, is that how do you do it on demand, right? So what is it? Formally speaking, when you talk about live migration, right? You take a virtual machine that is initially instantiated over one physical node and you move it to another physical machine, okay, without disrupting its software environment. That's the formal definition of it, right? So you take it from one physical machine, a VM that was instantiated on one physical machine, to another physical machine without causing any disruption to its software stack. And when I say software stack, we mean OS, any library and packages, and any applications that is running. Okay, just one moment. Yes.
Can you do that while it's being done?
Yeah, but there will be some downtime, but it will be minimal in nature. So we will talk about that on. Yes.
So without disrupting the image.
Without disrupting the image itself. Yes. And that includes, by the way, the data as well. The data that your application and processes might be generating, might be collecting, that also is present, part of it. You don't want to disrupt that. You don't want to lose that data, right? But again, remember, nothing is ideal. Doesn't mean that everything will be 100%. Right? But we want to get as close to it. Even cloud tells you that it gives you 99.9999%. Nobody's going to tell you 100. Even the doctor tells you, right? For the toothpaste, it will kill 99% of the germs. Yes.
If we are keeping the data on the same machine, is that the case?
No. So we might be taking it to another physical machine altogether.
Right, so then why we are worried about that data?
What do you
The
mean?
data resides on the other side.
Yeah, but if you do not migrate the data correctly, you might lose some of that data. It's not a database. It's with storage is connected to the VM. Remember, we are taking all these bits and pieces and we are connecting it to the VM instance.
Like volume is also kind of virtualized.
It's detachable. Yes, it is virtualized as well. Yeah, so we will talk about that. All right. So again, why do we want to perform live migration? Some of the conceptual points, nothing much to explain here, is that if your node fails, whether it is physical or virtual, it can fail over to something else. Right? Fail over means you can avoid a complete failure of your application. Right? So there will be some downtime, there will be some slowing down of your application, whatever or however you have defined your migration strategy. But some part of your service might still be available, right? So this can only be done if the new host where you're taking it to supports the OS distribution of the guest OS you are currently running inside of your VM. That is important, right? Because if I take it to an area where it does not support the OS distribution, which my VM requires, how am I going to instantiate it there? Right? So that template needs to be present wherever you're taking it, but you will very rarely hit this scenario where it is not available. Okay. Other than that, since failover strategies are there, it improves fault tolerance and recovery as well. Okay. The only downside that is there for your live migration is that the original VM need to give up all its responsibility. Okay. Now you might ask yourself, why is this a downside? Why?
Where's the stuff that's running gonna go?
Well, yeah, true, right? So what is already running, what will happen to that? Well, it has to wait a bit, right? That bit is subjective in nature as to how fast you can do the migration strategy, but there will still be a down. Okay, that one person that we are addressing, right? So we are essentially going to see how we can perform live migration, right? So it is essentially performed in 6 steps, 6 or 5 steps, actually 6, sorry. 6 steps, right? So I'm not going to read all of it line by line, but I'm going to explain you high level what happens, and then you will supplement this with the reading of your own, right? So the first stage till this point is where you start the process of live migration, right? The second step is to deal with the memory and file system, which is basically the bottleneck, all right? And then the third step is to set up the new environment, and the final phase is to stop the old environment altogether. That is to purge, right? So the first step is known as pre-migration, where you have an active VM that is running on, let's say, host A, and host A is actual physical machine, okay, wherever that might be. So remember, host A, physical, to B, physical. That's going per the definition of what live VM migration is. If you go back here, and you see, you move a VM from one physical node to another. So when we say here that we are moving from host A to host B, these hosts are physical machines, okay? So what you want to do is you can either pre-select where you want to move, that is, you can either pre-select where host B is going to be or what host B is going to be, or you can decide that dynamically as well, right? That depends on the strategy that you're using for copying here, and we will talk about that in a few slides, right? But this is the step where you decide that you need to move. You can either pre-select where you want to move, or you can let the virtual infrastructure manager decide where it needs to be moved, okay? The next thing is, when you have decided where it will move, eventually you have to make the decision, right? Then you need to reserve space there. So that means whatever resources that was being utilized by that VM on host A, you need to reserve that much resource on host B in order to instantiate and execute that VM, right? That is quite self-explanatory. There is nothing complicated that is happening here. The next step is where things starts to get a little bit, you know, I wouldn't say challenging, but tedious. It takes some time, right? And the time is with respect to taking all of that memory that you have on the VM that was running on host A and then moving that to host B. Okay, because when you think of memory, that is memory, the main, as well as any other additional storage units that is attached to that particular volume, right, or particular VM. How are you going to move it? What is the most intuitive way that you can think of? Okay. Anything else? It's right. Yes. What else? But remember, at this point, you have not terminated the original VM. So that means things are still coming, processes might be still running. So if you take a snapshot, it's only up till a certain point, but that point will bleed out of that. You will bleed outside of that point that you bleed. Snapshot is right. It's one of the three ways. There are two more ways. The one that you see in front of you on the slide is the second way, if you include snapshot to be one of the ways, and that is pre-copying. That is, you start the process of copying the memory and the file system as you are readying your move from host A to host B. That is pre-copy, right? So there are three ways. Let's put that three-way down. The first way to move your memory and file system, not just the storage, right? So we are bringing it together, is known as pre-copy. Okay. The second way is known as post-copy, which basically says that after you have migrated, then you move the memory and the file system from the old to the new. But that incurs additional overhead as well, and you need to reason with that. Okay. And the third way, which is suggested, taking snapshots, right? Better known as checkpoint and relay, or trace and relay. So together, the strategy is called CR-TR. Checkpoint, everybody understand? Creating checkpoints. When you create checkpoints, you create snapshots, right? Basically, an image of whatever the checkpoint or covers, right? Then you relay that information, or you trace it and then relay, right? So you have three strategies that are available in order to copy your memory and file system to the new host. So what we are looking at here is basically the process of pre-copying. Okay, so that is basically to start to copy it the moment when you have made the decision that you're going to migrate and you have reserved the resources on the other host in order to do the migration. So what do? You enable the process of shadow paging. Does somebody remember from last class what shadow paging is? It's not a ninja technique.
So paging that is on VIA. Where
Elaborate,
it's virtual memory and.
correct, yes. Right, so remember, when you have typical physical machines, again and again we discussed, we don't see the actual physical storage, we see a virtual layer on top of that, right? So you have the physical, then you have the virtual. So the physical needs to be translated to the virtual and vice versa. So if the user reacts with the virtual, that needs to be translated to where actually the physical is, right? So this is known as paging, essentially the translation, okay? And it is enabled through the memory management using and the translational look aside buffer, right? The TLB tables. But what happens when you virtualize memory itself? If you virtualize memory itself, think of this process happening inside a VM. But the actual hardware resources is somewhere down the hypervisor level, right? So this hypervisor needs to have an interaction with the memory. So for the hypervisor itself, there will be a virtual layer and an actual physical layer. So this translation that will happen at the hypervisor level as well as within the VM. So there are two stages of translation that is taking place here, right? So the bottom stage is known as shadow page tables because it is shadowing what is happening in the VM itself. That's where the name comes from, right? So the pre-copying process enables shadow paging and it starts to copy what is known as the dirty pages. Any idea what dirty means? Don't take it literally. You have to think in terms of, well, if you have done database with me, or if you have taken any kind of architectural class, we have discussed this. It is actually used. Yeah.
So dirty data means the data that is being modified but not pushed on the memory.
Yes, correct. Right. So basically things that you are changing, right, but you are not committing it. Right. So you have two different copies of it. So in the reason why I said databases, because this happens in transactions, right? When you have multiple users trying to access the same database resource, you might end up resulting in different copies of the data, which has not yet synced up together, right? In the memory, basically you're changing things, you have not yet committed, right? So you end up with those copies of uncommitted data, right? So you need to keep a track of that. That is where the problem lies, right? Because you have not terminated the original VM yet. So some processes might still be running, some requests might still be coming, right? So as you keep on copying, you will end up getting more and more new data. So here you can see there is a small cycle that goes into the iterative copy process. And this is the reason why it is called iterative, because you need to keep a track of these changes that is happening. But now the question is, when does the cycle stop? Because if you do not terminate the VM, things will keep on running. And if things keeps on running, you will always end up having some sort of dirty page, right? So you have to stop at some point of time. And this is where you should be able to appreciate why it becomes more challenging or tedious to deal with this memory migration and file system migration. Because OS migration is not a challenge. If the distribution is present in that other host, all I need to do is just plug it in, right? IO, not a problem. Network, still not a problem. Take some time, but it's okay. You can do that. This is where the problem is, right? When do you stop, right? Eventually, you have to make a decision where you have to pull that VM, which is running on host A, the original VM, out of commission in order to break out of this cycle, or you will never come out of the cycle by itself, right? When you do that, you suspend the VM on the original host, and then you make a ARP, which is known as the address resolution protocol. And this is with respect to finding its new address on the network, such that any new traffic will be sent to that new host B, where that new virtual machine will be running, okay? Here, you do not want any kind of forwarding or redirect. You just don't want that original VM to receive any requests. So in order to do that, there has to be an advertisement to all of the involved parties, either within the cluster or outside of it, to tell it the new location of this VM on host B. Okay, remember when you change houses, what do you do with USPS? You give them a forwarding request, right? So any letter that comes to your old address will be sent to your new address. But there is also a note that USPS gives you that if you do not update with the original people of your new address, we will not forward you past this unless you pay us. then we will do it for 1 more year, right? But you get the idea. Even they tell you that don't rely on this service, right? Otherwise, it will be problematic because you will go from that second new address to a third new address. What will happen? Your old address will keep receiving the mails? No, you don't want that. That consumes unnecessary bandwidth, right? So here, in order to advertise this new location's address, we invoke what is known as the address resolution protocol. That is basically a public advertisement of the new location, okay? Whatever the IP is, okay? So here, what will happen, this will generate 2 things for you. I say 3, but 2 things for you, okay? So basically, it will take the new virtual IP and the new virtual MAC, and it will advertise it to everybody else where to find this, right? So that way, when you send the new request, you will not go to host A when the VM was running on host A, and I will call this VM old, and I will call this VM new. Nothing against old and new people, but anyways, right? So any request will stop coming to this once it is suspended. And in order to not redirect, that's not the best word, but it keeps coming on. In order to send it to the new address, you basically will invoke the ARP, which will give you a new virtual IP, a new virtual MAC. Okay, machine address content and stuff like that. All right. And after that, you will suspend the host and then run the other machine normally. Okay. So we'll stop here and then we'll continue our discussion again on Wednesday. All right. See you online on Wednesday.
All right, thank you.
Bye-bye.